Hello students. Welcome back to class. Today, we are going to explore simple AC circuit. But before we get started, let's quickly recap what we covered in our last lesson. In our last class, we learned about the applications of electromagnetic fields, where an electric motor changes electrical energy into mechanical energy to power machines. A moving coil galvanometer measures small electric currents through the rotation of a coil in a magnetic field. And an induction coil increases voltage using electromagnetic induction for applications such as car ignitions and X-ray machines. Also, electromagnetic induction teaches us that Faraday's law explains how a changing magnetic field can generate electricity. The motor generator effect shows that motors convert electrical energy into mechanical energy, while generators do the reverse. And finally, eddy currents are loops of electric current in metals that can cause energy loss, but are also useful in devices like induction cookers and train brakes. Here are our lesson objectives. First, we are going to explore the nomenclature in AC circuits. Next, we will look at peak values and RMS values. And finally, we will study inductive reactance. Let's talk about alternating current, or simply AC. AC is electricity that changes its size and direction over time. Unlike DC, which flows in only one direction, AC keeps reversing direction at regular intervals. Now, here's something important. The most common AC waveform is a sine wave, also called a sinusoidal wave. It is a smooth, repeating curve that goes up and down, showing how current or voltage changes with time. When the wave is above the center line, current flows in one direction. And when it is below, it flows in the opposite direction. The highest point of the wave is called the peak value. And one complete up and down motion is called a cycle. Finally, the number of cycles in 1 second is called the frequency. The most common AC waveform is a sine wave. It is expressed as instantaneous current equals peak current sine of 2 pi ft. Or instantaneous current equals peak current sine of omega t. Here, the instantaneous current is the current value at any given time. The peak current is the maximum current value. F is the frequency. Omega, which equals 2 pi f, is the angular frequency. And omega t is the phase angle. Similarly, voltage is given by instantaneous voltage equals peak voltage sine of 2 pi ft. Or instantaneous voltage equals peak voltage sine of omega t. In this case, the instantaneous voltage is the voltage value at any given time. And the peak voltage is the maximum voltage value. Let's move on to peak and RMS values. First, the peak value, also called the maximum value. This is the highest value reached by the current or voltage during one complete cycle of an alternating current waveform. It represents the maximum strength of the wave. Next, we have the RMS value, which means root mean square value. This is the effective value of an alternating current. It is the equivalent direct current value that would produce the same heating effect in a resistor. In other words, it tells us how much useful power the alternating current can actually deliver. Now, for a sinusoidal wave, the root mean square value of current is equal to the peak current divided by the square root of 2. Similarly, the root mean square value of voltage is equal to the peak voltage divided by the square root of 2, where the peak current is written as I0. The peak voltage is written as V0. The root mean square current is written as IRMS, which means effective current. And the root mean square voltage is written as VRMS, which means effective voltage. A real-life example of RMS voltage in an appliance is the mains electricity that powers household devices. When we say a refrigerator operates at 220 volts to 240 volts, that number refers to the root mean square voltage of the AC power supply coming from the wall socket. Let's talk about inductive reactance. An inductive reactance is the opposition that an inductor offers to the flow of alternating current. It is similar to resistance, but not exactly the same. Here's why. resistance converts electrical energy into heat. Inductive reactance does not consume power. Instead, it only causes the current to lag behind the voltage by 90 degrees, without dissipating energy as heat. It is calculated using this formula. Inductive reactance equals 2 times pi, multiplied by the frequency, multiplied by the inductance. Where L is the inductance in Henry, written as H. F is the frequency of the AC supply, measured in Hertz. And XL is the inductive reactance, measured in ohms. Here's a real-life connection. Inductive reactance is found in devices like ceiling fans, electric motors. In these machines, coils of wire create inductors, and this affects how the alternating current flows, controlling speed, performance, and efficiency. You've completed this lesson, well done. Let's test your memory with a few quick questions, a fun way to check what you've learned. Today, we covered 3 important areas. First, the nomenclature in AC circuits. Then, we discussed peak values and RMS values. And finally, we explored inductive reactance. I trust you found the lesson both interesting and informative. In our next class, we'll continue with simple AC circuits, Part 2. Thank you.